Hello, colleagues. My name is Ihor Butko. I want to introduce you our presentation, Vegetation Zone Segmentation in Multispectral Imagery. Semantic segmentation of images using convolutional neural networks allows for the assessment of vegetation areas in multispectral images with high resolution. To improve classification accuracy, multispectral images utilized providing additional information for each pixel by supplementing color images with near-infrared channels. These channels contribute to clearer class separation and aid in distinguishing classes with similar visual characteristics, such as assigning a specified green pixel to classes like grass, shrubs, or trees. The issue of the versatility of the models used in practice is important. This paper shows the possibility of using U-Net-shaped architecture network, which is trained on a data set with aerial images to find vegetation zone in satellite images. For the validation of result obtained through semantic segmentation, it's essential to obtain a reliable assessment of vegetation cover area independently. To achieve this, the normal difference vegetation index, NDVI, proposed as a suitable metric. NDVI is a simple quantitative indicator of the amount of photosynthetically active biomass, commonly referred to as a vegetation index. The aim of the investigation is to consider the implementation of a semantic segmentation of 4-channel multispectral images using a U-Net-shaped network, and to assess the quality of segmentation of the vegetation zone using the calculation of the NDVI. As mentioned in original papers, the main idea of the U-Net architecture is to supplement a conventional convolutional network with a symmetrical path, where the pooling operations dimensionally reduction of objects are accordingly replaced by dimensionally increment operator that allowed increasing the resolution of the output. In the part in which there is an increase in dimensionality, there are many future channels that allow the network to spread contextual information to layers of high resolution. Therefore, the part in which the explanation occurs in symmetrical to the part of the construction, this gives a U-shaped architecture. Such a network uses only convolutions without any fully connected layers. To predict the value of pixels within an image's area, the missing context is extrapolated by additional processing, which look like a reflection from the point of view of network symmetry of the input image. This tiling strategy is important to implant the network to large images, as otherwise the resolution will be limited. The classic network architecture is shown in figure in this slide. In our investigation, we proposed expanding the number of layers in the U-Net network to 58, while maintaining the same architecture. This modification enables achieving satisfactory results for 4-channel near-infrared plus RGB images instead of requiring 6 channels, 3 near-infrared plus RGB images. In this picture, you can see images from the standard Hamlin Beach State Park dataset are shown in this slide. On the left is an images. On the left is an image used for training, and on the right side is images used for validation. Given the primary objective is vegetation detection, segmentation into 4 classes is employed. There are: first, it's water; second, it's vegetation; third is soil; and fourth is other. The result of semantic segmentation are shown in this slide. The sequence of images displayed processes as follows. First, the ground truth images is shown. Next, an aerial images with 6 channel is presented. And finally, an aerial images with 4th channel is displayed. Now let's define the standard segmentation quality metrics. First metric is global accuracy, is a ratio of correctly classified pixel, regardless of class, to the total number of pixel. It's used in case where a quick and inexpensive estimate to percentage of correctly classified pixel is required. The second is mean accuracy. Mean accuracy is the average of the accuracy score for all classes in all images, with accuracy indicating the percentage of a correctly identified pixel for each class. Used when you want to read how correctly each class defines pixels. The third metric is the mean IOU, average instruction to union ratio. The average IOU value for all classes in all images. Fourth weight IOU, weighted intersection to union ratio, is the average IOU value of each class, weighted by the number of pixels in that class. This metric is used if images have disproportionately large classes to reduce the impact of small class errors on the overall quality score. And the fifth mean BF score, BFC, is the average of the BF score for all channel in all images. Comparative results of segmentation quality for 6th channel and 4th channel images are shown in the table. The results of segmentation of 4-channel images are expected to be slightly worse than the result of 6-channel images, but are quite acceptable for vegetation zone selection tasks. For additional experiments, 4-channel satellite images of the region near Yanakievo Donetsk region, denoted as fragment 1st and fragment 2nd, were employed. A map of the area with marked area of interest is shown in this slide. Note that the satellite image is fed to the network input. to the network input without any pre-processing, so as not to change its statistic in relation to the images from the dataset that were used for post-training of the network. Result of processing for fragment 1 image are shown in this slide. The images are arranged from left to right as follows. In the original image, the label image, vegetation zone selected based on the vegetation class, and the selection of vegetation zone using binarizate NDVI. A result of processing for fragment second image are shown in this slide. We have demonstrated the process of semantic segmentation using a UNet-like network. Illustrate through the processing of both 6-channel aerial images and 4-channel multispectral satellite images. While the segmentation results of 4-channel images are anticipated to be slightly inferior to those of 6-channel images, they are deemed acceptable for vegetation zone selection tasks. Moreover, utilizing 4-channel images, notable reduced processing time. Of particular interest is ability to train the model with aerial images database, allowing its application to satellite images. The quality of vegetation zone segmentation was evaluated in comparison with the normalized difference vegetation index NDVI. Through analyzation, the result obtained, a strong correspondence was observed between the outcomes of semantic segmentation via neural network and NDVI usage. Thank you for your attention, and glory to Ukraine.